Hello, everybody. Thank you for joining this webinar today. As we're going to be discussing protection technical issues when implementing renewables and alternatives by Professor Akhtar Kalama, EIT Academic Board Chairman. Can please everybody disable the sound and pop-up notification by kindly please going to my settings, the cog symbol on the bottom right corner of the screen. If everybody can just do that for me, I'll be very happy actually. And go to the notification settings and untick all the boxes as you can see on the screen. Okay, thank you guys. The common questions frequently asked are copy of slides, video recording. Everybody registered for this webinar will receive a copy of the PDF slides and a link to the video recording within the next 2 business days via email. Please monitor your junk email folder. Certificate of attendancy. We provide a free digital certificate of attendancy for live attendancy for technical topic webinars. There will be a link, QR code to a short form survey provided at the end of this session, which you need to complete in order to receive one. Once completed, we'll endeavor to send you certificate to within the next 4 business days. Thank you very much, guys. Briefly going to tell you guys a little introduction about EIT, a bit about EIT if you are joining our webinar for the first time. We are one of the only institutions in the world specializing in engineering. We currently offer a range of industry-focused courses mainly across civil mechanical, electrical, and industrial automation engineering. For short courses all the way through to a Doctor of Engineering degree. All our courses are offered online and also on campus for certain courses, which means students can study from wherever they are in the world, but also experience studying engineering in Australia if they want to. All of our vocational programs plus high ed degrees are recognized and accredited by Australian government. But we also have a number of courses internationally recognized under one of the 3 international accords, Sydney, Dublin, and Washington. Thank you very much. I'll be passing the whole course to Professor Akhtar Kalama. Thank you, guys.
Thank you very much, my friend. That is me when I was young. I don't look that good anymore. But anyway, Jazz had my photograph and other things. So today, what I want to do is talk about 7 topics in this next 50 minutes or so, sorry, 40 minutes or so, because I want to spend about 5 to 10 minutes on question answers. So the welcome has been done, introduction has been done. I want to highlight what are the responsibilities of the network, talk a bit on embedded generation, and then you keep on hearing about distributed generation and some of the issues. In particular, I'll give you examples of the European one with what type of DG activities are happening, and then I'll conclude. If I get time, I will also talk about the issues that happen in Australia in 2016. But before that, a bit on myself. I, um, I'm really dedicated to engineering education and research. Naturally, I've got a lot of consultancy and collaboration work going, not only in Australia, but all over the world. I'm also the editor-in-chief of Australian Journal of Electrical and Electronic Engineering. I have a number of publications, and I don't want to talk about it. The best part is that I've produced about 49 postgraduate research students, and I need to get another one so that I can have a 50-run sort of score. I'm consultant for a number of ESI, electricity supply industries, and I also do a lot of change management plan through my consultancy group. I graduated from India originally. I did my 2 degrees in India, my original Bachelor of Science degree, then my Bachelor of Electrical Engineering, followed by the Master's in USA in Oklahoma, and PhD in Bath. I've worked in many countries and the 4 continents, and I've got a number of fellowship of various professional bodies. Now, with that thing over, let's come to the topic. My first thing is, what is the responsibility of a network? What do you think a network is supposed to do? What are their objectives? First thing is that they must supply the load. It must have the capacity to supply load. And then it must be capable of handling redundancy, especially security standards has to be followed. The third thing I believe is safety, fault rating of components, and ability to protect. Now, protection is a nightmare and is a very difficult thing, especially with all the renewables and alternatives which are in place. You find protection has become a very big issue. The most important thing is power quality. In particular, what happens to the voltage, the frequency, the harmonics, etc. And the adequacy of the reliability of network, how reliable the network is. So if we know those things, let us try and see what has embedded generation done. And if you look at this figure that I have, that this is traditionally a classical thing which happens now. As a matter of fact, this is the one that actually does most of the things. In particular, they talk about these things, all these embedded generation that you see. So, in fact, if you look at it carefully, what you find is that I better try and rub this off. Jazz, can you rub that off, please? Here it is. It is. Jazz, can you rub that off? The eraser is not working.
Okay, let me
Anyway,
solve it.
can you rub that off? I'm trying to rub that off. It's not getting out. This is the best way. Get it out of the system. Okay. But today's network, there is in the network itself, what we had, it was vertically operated. All the flow was in one direction. So you found that it's from generation, it went to transmission, then to distribution, and then to utilization. And it was all unidirectional. Later on, it is no longer that. Once we have a DG, and that has made a lot of difference because the flow has become bidirectional, tridirectional, all sorts of directions. In fact, the easiest way I can say is that two-directional, two-way boundary flows, which is there. So you can have sources which can be embedded anywhere in the network. They can all talk to each other. And there's a huge amount of DGs that are available with various types and characteristics. And they do have a lot of impacts on the network. So from unidirectional to bidirectional or multidirectional, so the whole philosophy of network has changed. In fact, there are many issues which are not at all understood. And this has impact on planning, operations, and safety. Now, what are the benefits? When we talk about embedded generation, what are the benefits? One benefit that I can think of is that you don't have to spend a lump sum of money all at one time. You can defer your expenditure on the network. Naturally, if you have embedded generation which is close to the load, your network losses are a lot lower. Your voltage level at the local level improves. And the most important thing in today's date and time, there is substantial environmental advantage. We are very concerned with the environment, with all these clean air, with all these various United Nations sustainable development projects which is going on, where there is a lot of concern about environment. Now, you will find that wind turbines are utilizing natural energy. This is natural wind energy. Solar cells are utilizing sunlight. And you find a lot of CHP, that is combined heat and power, or what we call cogeneration. And where you used to have 30 to 35% efficiency with a single cycle plant, and it went to a dual cycle plant, it went to about 50%. With a CHP plant, they're talking about 80 to 90% efficiency. And the thing which is the most interesting one is that this is the only way we can get our greenhouse gas emissions sorted out. So, naturally, cost is always a very important feature, and we as engineers are very concerned about the cost. One cost is that you need additional assets. The other cost could be operational and safety issues. And naturally, one cost, especially in the reign of deregulation and privatization, where maintenance has suffered, you might have to have more cost towards the maintenance. Now, renewables. Whether you like it, you don't like it, renewable is there. Renewable is the answer to most of the problem. Whether we have any fancy about anything else, you might be the best person who would like to promote fossil fuel. You will find that there will be a lot of backlash against you. So renewable is the answer to many prayers of many of the people who are concerned about the health and environment. And renewables are the major driver of distributed generation. So some people see renewables as providing, increasing proportion of energy of world energy resources. And to give you an example, in Australia, 78% of our energy comes from fossil fuel plant. And slowly and steadily, renewables are taking place. And we expect in 2030, we will have between 30 to 40% of our energy being produced by renewable energy plant. The present government, which is there, is talking about 2050 to have 100% renewables, and we will get rid of all our fossil fuel plant. Whether it be possible or not, but it's a fantastic goal to go for. And I kept on getting these questions all the time, that in developing countries, we need energy. We don't care about the environment. That's how it all starts, right? But there's no doubt about it that at least those people who are starting or want to get more energy, they have a better option now with the renewable energy. Now, one of the things that used to happen in the past, whenever we used to do cost comparison, I still remember when I started working on PV area about 20 years back on photovoltaic and all, um, I could not produce energy at all cheaper than that which is coming from a coal-fired plant. A generation cost of the coal-fired plant is anything between 2 to 4 cents a unit, whereas a renewable at that time was about $1 a unit. So that was nowhere on the earth it would have gone at. Now, both the cost and performance are dramatically improved. As a matter of fact, in particular, the wind energy is comparable to the cost which is being produced by coal-fired plant. So some of the countries which has got fantastic growth in the last decade are China. China has become a powerhouse of renewable energy. They can supply all the PV panels of the whole world. Denmark has been very good. Germany is another good example. These are the landlocked nation and they need energy and they don't want to use their nuclear plant after all the accidents that has taken place. India is another country where there is a lot of talk to you about. 80% PV and wind energy capacity is with them. So what? But people have this impression that the only energy that we have got is basically the the PVs and the winds. Man, I have to tell you, things like solar thermal is there, hydro is there, geothermal is there, methane extraction is there. We are working a lot on methane extraction at the moment, especially for hydrogen plant. Biomass, can't we convert all the waste that we have got and convert that into energy? The marine cogeneration, as I mentioned, and there are many other I have not mentioned about the ocean and other things. There are so many various type of way you can produce energy, especially renewable, where there is zero or practically zero emission. Now, the thing is can I challenge this DG? Can I challenge distributed generation? Can pure economy of scale but local production offset large scale base power? In Melbourne, where I am, there is 2,000 megawatt of plant over here in Latrobe Valley, about 80 to 100 kilometers away from Melbourne. Can I have small scale, right, of local production? Can this be replaced? What about network losses, especially in local generation? I did tell you network losses are reduced. Now, many people believe that renewables have got strength because there are incentives, and the incentives are being provided by the governments. What happens if the incentive goes away? Or should there be a focus on end user efficiency? Or should we be looking at a new paradigm? One of the things which is often talked about is carbon taxes. In Australia, I can definitely tell you that we had a prime minister, Gillard. When she was a prime minister, she introduced carbon taxes and she lost her prime ministership purely because of that. Not very popular at all. Now, what happens to nuclear? Is there any scope of getting back to nuclear? That is something, it's a very interesting debate, and I don't have the time to go through each one of them, but that's an interesting debate. Should we look at it? Now, I did say that there is a target. European have done better than us, especially in Australia. Okay, they set up a target of 20%. Okay, there they looked at 20% now, and by 2030 they will go for around 30 to 35%. And as a matter of fact, they could revise this figure to about 40%. And you can see how the target, everywhere there is a target, you can look at it, which is beyond that red line that you see, is a 2020 target. And all that has been achieved. The thing which I wanted to say was that which is the main form of renewable energy which is compatible or comparable to a fossil fuel plant, and which is price wise it'd be good, and that would be wind energy. But a problem is that there is a fluctuating power source. Also, it's intermittent in nature. If there is no wind, there is no wind power. Very simple. So you can see how the fluctuation takes place. Now, I think that both solar and wind technology will undercut electricity generation. So you will find that both coal and gas will disappear. As a matter of fact, even today, when I was taking my lecture for my master's student, I was talking about gas plants and how there's acute shortage of gas plants in Australia. You'd be surprised. In Australia, we have enough gas to supply the whole of Australia. So to tell me that because of COVID there is no gas, that I believe is rubbish. To tell me because of Ukraine and Russia war there is no gas, I think it's all rubbish. The only thing is that gas is being exported overseas from Australia, and the domestic market does not get gas. Although there's price parity between the domestic and international one. But exporters find it easier to sell it overseas than to sell it domestically. There's one state in Australia, which is Western Australia, where there is a capacity building exercise by their legislation, where you have to store 20% of gas in Western Australia before you can export it. So that way there is abundance of gas in Western Australia. Now, wind turbines. Look at the height of the wind turbines. You can see how big the wind turbines are. We are talking about huge heights. And to give you an example, look at this. This is the Washington Monument, and that is how in 2030 the wind turbine will be in that shape. Exactly in 2030, there's another expectation that the wind turbine will be greater than the Washington Monument. So you can see that, and the size of the wind turbine. Look at the size of the wind turbine, 11 megawatt by one wind turbine. So they're getting bigger, my friend. And if you compare that with Statue of Liberty, this is where the Statue of Liberty is. And this is a cruise ship. Can you see how the thing has changed? So if you look at hub height, if you look at rotor diameter, if you look at power, wind turbine is big. And if you want to order wind turbine, you will find there's a waiting queue for a long period of time. You might have to wait 1, 2, 5 years. Europe has done a fantastic thing. They have integrated their renewable energy source. And there are 8 countries, which is the Baltic countries, which is Poland, Germany, Denmark, Sweden, Finland, Lithuania, Estonia, and Latvia. They have joined a declaration there with the Commission so that they can accelerate new offshore wind. So in that whole region, if you look at it carefully, they're looking at making more and more wind turbine. And another thing is that these are not onshore wind turbine. They're getting the best out of it by using offshore wind turbine. And they're using that, in the North Sea. And this is the same thing happening in UK too. Now, the impact. If you look at the impact, there's going to be large load flows. And this is what is going to happen. There will be large load flows, which will affect the neighboring transmission system. There will be grid congestions and bottlenecks. And you will find there may be reduction of cross-border trading capacities. So interconnection has to be reinforced. And that is one of those best things that's going to happen. We'll have to look at interconnection. Whether the interconnection will be the same, whether we'll be going for HVDC, I don't know. There is a trend to go towards HVDC. So if you want to look at the consequences, you have to look at what are the developments of transmission and distribution system. Then you look at the impact on the power system's operation and control. So this is the first is development, the second is impact, the third is the consequence on the price. Because you have to take into consideration external effects of environment. And one thing we have forgotten completely, the storage devices. And we have to look very carefully at the advanced and conventional storage electrical devices. So therefore, if you look carefully, you have got a completely new energy revolution. And this revolution is going to cut your energy-related CO2 emissions. Whether you use CCS scheme, whether you use nuclear, whether you use renewables, whether you use the fuel switching, whether you use electrical efficiency, you will find that you will have to decarbonize the power sector, and this will bring the emissions back to the current level by 2050. So you have to achieve a 50% cut. And if you want to do that, don't forget, I have not mentioned anything on the transport sector. You have to look at that very carefully. So there's huge amount of opportunity. And let us see, if it is a wind generation, what sort of emissions are there? There is CO2, there is SOx, there is NOx, there is mercury. Okay. And these are the wind generation that you see, the annual reduction because of 1 megawatt of wind on the CO2 level, on the SOx level, on the NOx level, and mercury level. Now, if you look at LCOE, we're at levelized cost of electricity. And if you look at that thing, IGCC, that is integrated gasification combined cycle plant. Or you look at NGCC, which is the natural gas combined cycle combustion. Or you look at the pulverized coal combustion. So you find that the current combustion-based and gasification-based power system is not congenial to make your LCOE into a reliable factor. So, in the short term, everyone is talking about wind power, especially wherever there is electrical deserts. You need new links so you can connect that to the main grid. Wind power can substitute thermal units load closer to the load. That means there'll be change of usual flow. You need some sort of reinforcement of the main grid. And the example of Germany is very good. They have done a very good job. Now, what are the technical challenge? So what I'm trying to suggest is re-engineer the European power system. How can we do this? So first thing is to define the basic technical principle. That is the respective part of AC and DC. Do the feasibility of DC multi-terminal link and look at the evolution towards DC network. Find how flexible it is, how reliable it is, and look at the control section. Now, what are the consequences on onshore grid development? Because there will be concentration of large intermittent infeeds. So you need a European level type of plan where you can have a coordinated effort. What is the challenge for Europe? Onshore and offshore wind development is there. And they also have their thermal generation fleet. So European grid is entering into a new era. The transmission system operators coordination, TSO coordination, is a prerequisite so that they can have an adequate European grid. They have to speed up the approval procedures so that new grid infrastructure is a condition to meet the energy policy objectives. However, you need innovative solutions. You might have to look at undergrounding, as I mentioned it earlier, HVDC, a lot of things like that, fact devices. So you have to have an offshore grid which has more of an open frontier. But there'll be a lot of issues, especially regulatory, financial, legal, etc. issues will crop up. I did talk about storage, and I want to talk about storage a bit. And the reason I want to talk about storage is that if you look carefully and you look at a household, a very simple household, if you have only a PV without storage, it defeats the purpose of the PV. You can have a better return if you have both the PV and batteries. At the moment, as I'm talking, the battery prices are high, the inverter prices are high, which is making it difficult for residential customers to go for both PV and batteries, although that is the ideal conclusion, ideal suggestion. So if you want to manage the intermittency of wind and solar energy, and I'll tell you that in a minute toward the end of this presentation, what has happened in Australia, that we did not have any way to manage our wind and solar energy, and there was a blackout. So we need to manage load fluctuation, especially when we are supplying a peak consumption. So solution is very simple: storage. So you store your energy as an electrical energy and use it whenever it's required. What the constraint? The constraint is that technologies. Are the equipment available? And what is the life cycle of that? And what is the cost? As I told you, the cost is definitely an issue. Operating costs like losses, maintenance, and others are other issues. Now let's see some of the benefits. As I told you, it can accommodate intermittent generation. So it allows it to operate at peak load and efficiency by storing surpluses. So any surplus you have, you charge your batteries. It has the ability to dispatch energy during times of peak demand, that is peak load management. It can supply your peak demand locally and reduce transmission line demand. So therefore, the transmission line congestion is avoided. It has the ability to provide voltage support, the voltage regulation, voltage sag compensation, flickers, and other power factor correction. It has the ability to provide other ancillary services like frequency regulation, black start, reactive power. And there's also a possibility of islanded operation. And the best part is that it has the ability to perform arbitrage on electricity prices. Therefore, it has the impact on electricity markets. So when we are talking about storage, people do ask me, what type of storage are you talking about? Is it electrical storage? Is it magnetic? Is it mechanical? We can consider any one of them. If it's electric storage, it's the electrolyte type battery, that is lead acid, lithium ion, etc. If it's a flow batteries, is it a vanadium, redox, zinc bromide, etc. Is it capacitors and supercapacitors and ultracapacitors? The magnetic storage, which could be SMES type of system, where the superconducting magnetic energy storage. The mechanical storage could be flywheels, compressed air, or pumped hydro storage. So if you look at the operating time frame, you find that there's all sorts of technologies which I can get. And all these has a capacity of over 100 kilowatt. In the short term, you can look at these. In the long term, you can look at this. My friend, sodium-based batteries is an area to watch. So there are a lot of projects which is currently in the pipeline where they're looking at all sorts of battery combination. Okay, what sort of power rating we are talking about? Look at the redox, look at that sodium type, the compressed air type, lead acid, which is here, and the SMES type. So there are some limitations and opportunities. One is that, as I told you right in the beginning, it is expensive, my friends. We have to reduce the cost. Although the cost is coming down, I must admit that. The life cycle and asset management has to be worked out. And you have to determine what happens under severe environment condition, what impact it has on the lifestyle. So you need to build a business case. Are you going to store, or you are going to directly use electrical energy? What sort of losses I've got? You have to do the complete cycle from storage to retrieval. Amortizing the capital and operating costs, that means you look at decapitalizing the losses. And look at what sort of electricity cost is there. So you can compare, you have to compete with low production cost in large scale generating plant. So there is business opportunities, my friend, especially where there's a remote location and new development. That means there's no electrical infrastructure. Battery is definitely a thing to consider. Or there's new installation which requires high power quality and reliability. So the other option which we are doing a lot, I mean, I'm working on this area, which is hydrogen storage. We're going to use the gas pipeline to transport hydrogen from Australia to our neighbors in Asia, whether it's Japan or other places. But you can see we are looking at different types of hydrogen. Is it going to be green hydrogen, blue hydrogen? No, but one thing is for sure. more than 50% of the wind energy in a given configuration is wasted or dumped. And they cannot be absorbed into an isolated diesel grid. This excess energy can't we use that for hydrogen production? Hydrogen fuel continues to the firm power ability to the community. So therefore, you can get hydrogen from wind energy. And definitely the cost will not be as much as people think, because at the moment the cost is very high, especially in non-American countries, which is 4 to 6 times. So hydrogen can be an energy storage, and this has an advantage because there is no emission in it. It's free from any emission. There's no IC engine, right? It just has the fuel cell. You can transport that. You can use gas pipeline. You can use ships. You can use all sorts of methods to transport from a long distance. There are issues, I do understand. Overall process, that means from generation to storage to consumption. What is the efficiency? What happens to the integration of multiple energy sources? How much availability of the technology and commercialization issues are there? So, if you can think of integrating both the wind and hydro, there are issues of power balancing. There is wind penetration has limits, especially below 10% and above. The nature of the hydro reservoirs, especially storage, where are you going to do the storage? Yearly, or is it going to be multi-year reservoirs, or are you going to use pump storage? So wind power integration issues are there because our transmission is not capable of handling that. That's why I said interconnection might be a big issue. Integration also can be a big issue because you cannot do the power balancing. So there is an impact of wind integration, and you need to mitigate by means of precise wind forecasting session. So you need to find what is the impact on real time and day ahead the market operation. So there is operational constraint, and the operational constraints has an impact on hydro plant efficiency and life. Now, what are the technical issues? And there are a lot of technical issues, my friend. Not small, lot of them. Maturity of technology, network design, network operation, electrical protection, variety of technologies, connection cost, role of ICTs, network capacity, power quality, Q and V control, especially in the impact on weak systems, reliability, impact or benefit to security, islanding safety. So there are so many issues that I have got. There's about 12 that I have listed. Let's see something. I talked about maturity of technology because technology is still developing. And, it takes time to have a fully developed system. Remember, my friend, we have got some very important tool, power electronics. Power electronics could be a very important tool. But people are still searching for that magic bullet. There are many applications who are looking for storage. Storage is, the application is not a problem. To find the right technology is a problem. We're talking about supercapacitors, and they are providing new dimension. As a matter of fact, they're looking at in electric vehicle, why not use supercapacitors? So the design part, the network design, there must be a capacity of network so that it can accept connection. The short circuit capacity, especially when you increase the synchronous machine or decrease the power electronics. What are the performance of switch gear? How will the power flow? Network operation, You have to know the location of embedded generation. Right through capability during fault, that is one of the big problems. And LVRT doesn't work. It is becoming a very big issue, especially when there's high penetration. And I'll give you the example. And synchronization. Protection, oh, that's a nightmare. Nowadays, protection without communication has got no meaning. So you need to have adequate communication. So when we are talking about protection and communication goes hand in hand together, because you have to communicate the information of the protection state to the other part of the system. So you need technology which has got a smart relay protection. You must remember we have got smart grids. The protection is also very smart. So the power flow directions and voltage conditions has to be considered. Operation of network protection can occur. Fault level dependence on mode of operation can occur. Technologies, I said, variety is there. Wind is there, solar is there, gas turbine is there, fuel cells is there, micro-turbine is there, gas and diesel engines are there. Right? This is the DFIG. A very good introduction to technology using a synchronous generator and utilizing it with wind turbine. Connection cost. This is difficult part. A lot of negotiation has to be done. There is shallow, deep, or mixed connection cost. It is difficult, especially in a competitive market. And you have to look at how we can participate in ancillary services like spinning reserve, reactive power. Generally, it's all difficult. The role of ICT. Many of us are doing work in ICT at the moment. A lot of research going on. Optimum voltage control based on integral control of all the voltage controllable equipment in the grid needs to be done. We need to have technology that can utilize embedded generation as a reliable source versus a centralized control. So you need to research on the configuration of distribution systems so that you can utilize embedded generation. Power quality, an important issue, because it depends on the energy source and conversion technologies. You're going to have flicker and voltage fluctuation. That means there could be slow voltage variation, there could be fast voltage variation, there could be variability in primary energy source. Harmonics and interharmonics can come into play. Unbalanced situation. So you have to look at the standards. Australian standard 61,000 is a good series to look at. Look at the reactive power and voltage control. What happens if the wind farm is connected and wind farm not connected? When there is a connection of EG changes the voltage profile. So also is the flow of active, the P and Q changes. Now, reliability depends on the level of redundancy. Security of supply is a very big issue, especially solar. In places like Melbourne, where we don't have too much sunshine. Wind, where it's very unpredictable. So you have to look at the energy source or look at the capacity. And it all depends on the philosophy, the design philosophy, and whether, if you can run it on an island mode, whether that will help or not. The impact is very hard to gauge what is the benefit. I think intentional islanding helps, but it all depends on the reliability of the fuel source. So islanding, traditionally utilities do not allow islanding if they don't want to lose their customers. They want them to be connected to the system. But microgrids are more focused on islanding, and remote locations are with embedded generation. So issues of synchronization comes in, power quality comes in, energy balance is required, safety is. So more research is required in that area. In summary, what I've said is embedded generation or distributed generation area. There's intense activity going on, and there is interest worldwide. I know I'm part of the CIGRE B5 committee, and I can tell you there's a lot of emphasis on this issue. The European community is moving to a greater application of renewable energy. Practical economic implementation remains a challenge. Reviews are being carried out of issues associated with connection to the embedded generation. And there have been a lot of examples where you can demonstrate that. The future definitely is definitely going to change. I wanted to talk about this Australian one. In 2016, we had a blackout in South Australia. And this was due to weather condition. It damaged electricity transmission line and distributed network. At that time, 40% of the energy in South Australia was from renewable energy. Because of that weather condition, the wind damaged 23 pylons on electricity transmission line. And that was connected to Victoria. We were supplying 500 kV to South Australia through a 500 kV line. The entire state did not have electricity for 2 days. And supermarket was suspended for 13 days. And I want to emphasize 40% of the energy came from renewable in South Australia. South Australia was mostly dependent on wind energy. There was no proper planning and integration to divert or utilize the generated power. Now, how did we get over that problem? We had Elon Musk who came and put in 3 months a 100 megawatt battery. And that was the first step. At the moment, there are a lot of discussions going on, the interconnection to be HVDC or not, because South Australia is being supplied by 2 states. One is from Queensland and the other is from Victoria. And South Australia is a great example of renewable energy being used much higher than what the Australian renewable energy was required. And all the politicians said that it was the fault of the renewable energy that this occurred. It had nothing to do with that. The LVRT operated and protection failed, and Victoria and Queensland shut off. Victoria was first to shut off supply to Queensland and to South Australia. Queensland followed. And all of a sudden you find that the state was without power for 2 days, which is absolutely not acceptable in today's age and time. Jazz, can I give it back to you? Thank you very much.
Thank you very much, Professor Abdul Kalam. That was a lovely presentation. And I'm going to discuss our upcoming webinars, which, as you can see, the name is CFD Simulations of Supersonic Intake Ducts. If you want to join, you're more than welcome to join. You can go on our website. As you can see the link below, you can go and see more upcoming webinars. These are our upcoming EIT courses: professional certificates of competency courses, short courses throughout the whole year. That's when they happen. Diploma and advanced diploma courses too, undergraduate certificates, bachelor's of science degrees, graduate certificates, masters of engineering degrees, doctors of engineering, on-campus bachelor's, masters, and doctors of engineering programs. You can also find us on our website. As you can see the link below, you can see more scheduled courses that we have upcoming. Thank you, guys. Then the certificate of attendance, you can find it. I'll put the link in the chats right now. And To receive your digital certificate of attendance for participating in this webinar, please fill out the form and survey here, as I'll send the link right now. That's the link to the survey. And certificate of attendance will be sent out in the next 1 or 2 business days. And if you have any questions for Professor Akhtar Kalam, please do ask in our chat box. Thank you very much, guys.